Hello and welcome. In chapter 13, we have covered combustion, where the product's composition of a reaction is usually given. Thermodynamic concepts can be used to predict what the product composition would be through a chemical equilibrium analysis. That's what is done in chapter 14. So the difference between combustion and chemical equilibrium analysis is that here we do not know what the products are or what the composition is, and we can use first and second law of thermodynamics to predict that as a system reaches equilibrium, what the composition should be. So we have talked about chemical equilibrium with regards to closed system in this particular video. So it'll be a good idea to go over this video in conjunction with the current one, which I'm recording on open system, open reacting systems. The concepts are very well established. Suppose we have a system which is going to equilibrium. In this case, is shown as a closed system. It could be a working fluid flowing through a reactor. For instance, here the working fluid is CO2 flowing through a reactor subjected to a specific pressure or temperature. Then it can be shown that the reversible work, the work that you can extract out of the system, the maximum possible work, useful work that you can extract when the system equilibrates. Equilibrium means all the differences in the system is disappearing, but a difference can be always used to produce work. And as a result, as you produce more and more work, the system reaches equilibrium. That means there is nothing you can exploit any further from inside the system. There is no pressure difference, there is no temperature difference anywhere. There is no chemical potential difference anywhere. So it can be shown that maximizing the reversible work corresponds to the minimization of Gibbs function. So that gives us the equation that to find the equilibrium composition. So for instance, when CO2 is flowing through this reactor and it's subjected to very high pressure and temperature, you can choose any number of possible compounds, possible species that can be present in the product. So here, in this simple situation, we just show CO, an incomplete combustion involving CO. But there could be oxygen atom, there could be ozone and everything else possible between C and O, made from C and O. Anyway, once you pick up all this a list of species, the idea is that we find the Gibbs function at the given pressure and temperature the mixture is subjected to, in this case 3000 Kelvin. And then the Gibbs function is calculated for all possible composition, and the one that it minimizes Gibbs function is the equilibrium composition. So so to solve an equilibrium problem, you have to pick all the possible products species that you think is present. Of course, once you have a big list, then you can find some species that are so minute that if you delete that, it doesn't affect any of your solution in practical term for energy balance or entropy balance. Okay, so let's get started with a quick problem. Suppose we have equimolar oxygen and nitrogen flowing into a reaction chamber, and we would like to know the equilibrium composition at a given temperature. So this is like evaluating a state. You can go to the flow state and click on the NIGE. Okay, so let's build the reactants that is flowing in. So this is set as kilogram, the basis. So let's go to kilomole. If it's equimolar, suppose 1 kilomole of nitrogen and 1 kilomole of, by default is 1. You can of course change that. So this is my composition of the reactants that is coming in. And in the products, we can, oxygen and nitrogen, in this particular case, can produce all of these. Of course, there can be even more. NASA equilibrium program can give you 100 different species here. But let's say we click on all these probable species and we add them. And we want to know, so our goal by equilibrium composition is to know what are the kilomoles of each of these in this reaction. We want to produce this balanced reaction. Of course, in the in the reactants, we have nitrogen and oxygen atoms, and we see that they, of course, have to cover all the atoms of the reactants. We go to the state panel, and we pick up a temperature and pressure at which they're coming. Suppose they're coming at 100 kPa. The reactant is coming at 100 kPa, 300 Kelvin, and it picks up the mass flow rate from the reaction that we produced. But you can suppose we say no, the mass flow rate is really 1 kg per second of the reactant, so you can change it here. So the composition remains the same, equimolar oxygen and nitrogen, giving you can see the molar mass is average between nitrogen and oxygen atom, and you can see the different properties of each species in this mixture, the partial properties. For state 2, suppose the pressure is the same, 100 kPa, and let's say we're subjecting it to 2000 Kelvin of temperature. Notice that m dot 2 you cannot specify, it has to be exactly the same. So after the equilibrium composition is calculated, mass better be same as 1 kg per second. So we click calculate button, and notice that all these species amount, the partial pressure and the properties are listed here. And of course the mass flow rate is 1 kg per second. If you go to the composition panel, you'll see the detailed composition of the products are displayed here. Of course, if you click the super print button, you can get a printout of all that, what the particular reactions. This is the product composition, as you see. This is the reactants composition, etc. You could go to the state panel, and suppose you say, you know what, the temperature is different, or what the pressure will be, how the pressure will be affecting the solution. You can do all kinds of parametric study. But there is no super calculate button. You have to recalculate because it's quite complicated calculations that is involved here. Okay, so let's quickly go over one more problem, this time involving combustion. Open steady reactors will follow the open system, open steady specific branch, and combustion and chemical equilibrium. And here is my chemical equilibrium analysis tool. We'll click there. And of course, there'll be examples on this page. There are a number of video examples here. And this is where we launch the app. Notice that for combustion by default, it is kilomole. You can of course choose, suppose we have 1 kg of methane and 1 kg of oxygen coming, then we could choose kilograms. Anyway, so let's say we are burning gasoline, and we'd like to know, what is the, if you know the inlet and exit state, how much is the heat transfer. Let's say we have a burner where gasoline is burning. So let's find octane, which is like a surrogate for gasoline. Here is octane. It could be liquid octane, or let's take gaseous octane. We add that. So we have a kilomole of octane, and then we have let's say we could specify oxidizer, but instead of specifying, we could say air, but we can directly choose from here the standard reaction. Suppose equilibrium combustion with excess deficient air. So gasoline is burning with air. It could be burning with pure oxygen, or it could be burning with user-defined oxygen and nitrogen combination. So we'll just click here, and let's say it's theoretical air. So that's 100%. So this is the reactants. So we now know the reactants is methane burning with theoretical amount of air and producing products that we don't know yet. The air fuel ratio is 15 kg of air is needed for 1 kg of gasoline. Okay, it's not methane, I'm sorry, did I say methane? This is octane burning with air. Okay, so by default now that we have 100, a huge amount of mass is coming into the reaction chamber, but if you look at the amount of octane coming in, it is 114 kg. So if you have 1 kg of methane octane burning, then you can multiply the reaction by 1 over 114, and then we'll have so let's leave it on mole basis. So let's see 1 kilomole of octane is flowing. So we are making up a problem where 1 kilomole of octane is flowing with theoretical amount of air into a reaction chamber. Let's say they're going at 100 kPa and 300 Kelvin. And notice that the mass flow rate will be picked up from the reaction. So therefore, if I calculate, it is a whole lot of mass. That's 1 kilomole of octane plus all the air. That's why it's such a huge number. That's what is coming in. It's a pre-mixed reaction. For state 2, suppose the question is they're going out at 1000 or 2000 Kelvin. What will be the composition? So we do before that, I'm sorry, we forgot that the product, we have to figure out what should be in the product. So we go to the products panel and pick up. You can pick individually what you want, or the typical product on combustion are selected here. A lot of research studies has shown these are the typical hydrocarbon products. So when you burn fuel, hydrocarbon. And so now the reaction becomes a little more concrete. We've picked up what we want in our products, and we want to find the amounts. That's when we go to the state panel. State 2 is heat to products, and we say temperature is 100, and temperature is 2000, and it is going to do the calculation and minimize the Gibbs function, and found that the partial pressure of each species, all the properties of each species in the mixture. You can go back to the reaction panel and see the pure composition of the mixture here in graphical terms, as well as as a complete equation. Obviously, it's too many species, that's why it looks so weird. So now that we know the properties, like we know the mass flow rate, we know the enthalpy. So if the question is, determine the heat transfer that is going on in this combustion chamber, state 1 to state 2, and there is no work transfer, obviously, no external work. So you can see that there is a huge amount of, let's go to megawatt, because it's a huge amount, a kilomole of gasoline is a lot of gasoline. So you can see that so much heat is being transferred. So obviously, even though the products leave at 2000 Kelvin, heat is lost from the chamber. To find the adiabatic temperature, for instance, what is adiabatic flame temperature? When there is no heat transfer, the chamber is adiabatic, all the heat release goes into heating the products. Of course, in that case, the product mixture is going to be different, the composition is going to be different, and the temperature at the exit is going to be different. So let's say we don't know the temperature, so we recalculate this state and come back. Oh, sorry, it already updated the calculation. So in the device panel, let's initialize state 2 here. In the device panel, let's set up heat transfer to be 0. So what it does, it is now going to substitute. We should have entered the pressure because temperature is 1, which is unknown. And so it goes and calculates now, and determines the temperature to be 2273. So that is the adiabatic flame temperature. In other words, this is the temperature that will produce a heat transfer of 0. If you go to the I/O panel and if you directly calculate Q dot, you will find that will be very close to your answer. So it's m dot 1 star H2 minus H1. That is what is the heat transfer. And even though it looks big in kilowatt terms, it is very close to 0 compared to the heat transfer. In terms of the enthalpy, this is very close to a correct solution.